Okay, up to this point, we've dealt mainly with angles that are between 0 and 180 degrees. And what we're going to be doing in this lesson is starting to talk about angles of rotation, angles that are bigger than 180. And we know that when things rotate, that if it spins 360 degrees, it's spun all the way around. 720, 1080, all these angles are actually possible. So that's the angles we're going to be talking about and how to graph them in standard form. And let's start there. And then we'll talk about how they relate to actually trigonometry. So angles in standard form, we're actually going to graph these angles. And it says an angle on the coordinate plane, and that's that same XY coordinate system that we've always graphed on. An angle in the coordinate plane is in the standard form when the vertex, and that's the actual intersection point on that angle, the vertex is at the origin, and that's the 0.00, and one ray lies along the positive x-axis, and that would be here. The ray on the x-axis is called the initial side. And then we're going to rotate from there. And the other ray, wherever we rotate to, the other ray is called the terminal. With the same root as the word terminate, the word terminal, terminate means to stop. So that's where the actual ray stops. So, excuse me, the angle stops. So the angle starts here and it rotates and it stops here. Counterclockwise rotations, which that's what we have here. Remember that when you're dealing with a clock, that clocks rotate this way, that'd be clockwise. So counterclockwise rotations are positive angles. And clockwise rotations, which would be in this direction, would be negative angles. So we can also have positives and negatives when we're dealing with angles. One full rotation is equal to, we talked about that a while ago, 360 total degrees. Okay, next we're asked to actually draw some angles. It says sketch an angle with a given measurement in standard position. Now I do want to remind you that we're always going to start on the initial side along the positive x-axis. So here's our starting point, and we rotate from there. Now if we're rotating in this direction, just quick reminder that this is 90 degrees, 180, 90 more would be 270, 90 more than that, all the way back around would be 360, and we could actually keep going. 90 more than that would be 450, so 450 and 90 are the same angle. We'll talk more about that in just a second. But as we're sketching these, and just keep in mind that these are not exact, we're just getting kind of close, we're sketching. So 75 degrees, we know that right in the middle would be 45 degrees. So 75 would be somewhere right along in there. So there's your 75 degree angle. Notice that that was positive as well, as we have a negative angle on our second one. So we're again starting at 0 degrees. And since it is negative, we're going to rotate in the negative direction. This would be a negative 90, a negative 180, and that's plenty far enough. So instead of going all the way to negative 180, we're only going to negative 160, so we're 20 degrees short of that. So I'd say it's about right there. So there is your angle. Let me draw a little, there we go, to make it look a little bit better, just to show also the direction that we rotated. 430 degrees. Again, we start along the positive x-axis. We have 90, 180, 270, 360 is all the way back around, but we need to go farther. And what we can do is, how much further do we need to go? If we subtract it, we need 70 more degrees. So that's going to be, again, very similar to the first one, about right there. And the way I would draw that is we went all the way around, and then we went a little bit further. So I draw that little circle just to show it's not 70 degrees, it's 430, even though they look just alike. There was 75, and you can see that looks very similar to our 70 degree angle there. Okay, next up we're going to talk about another way of measuring angles. Up to this point, we've always measured our angles in degrees, but there is another unit of measurement. It's called a radian. Now, let me define what a radian actually is. And they've got this, this nice drawing here that I can use to actually define that. A radian would be, okay, we all know that this is a radius in a circle. If we were to take a radius of this length, okay, of the length you have right here, and actually wrap it around the circle to where this is also the length r. It's the same length. So we have a radius here, which would be the same as this. So if you were to wrap that radius, this angle right here that was formed would be 1 radian. And no matter how big the circle is what's cool about it. No matter how big the circle is, this angle would be the same angle, no matter what size circle. So a radian is a unit of angle measure based on arc length. And you see the arc that I drew on that last one. 1 radian is defined as the measure of the angle formed when the radius is equivalent to the length of the intercepted arc. And I know that sounds a little confusing, but the radius, same as this radius, is the same length as the actual arc. Okay. Recall that the circumference of a circle is 2 pi r, or 2r times pi. Therefore, we can do this. 360 degrees all the way around. We need to remember this. 360 degrees is going to be the same thing as 2 pi radians. That's going to be one of our conversion factor. If you were to take and go all the way around a circle, okay, that's the same thing as 2 pi on the radians. Therefore, 180 degrees would be half of that. So 180 degree would be pi radians. And that's going to be very important that we remember those two conversions, that's how we're going to end up actually converting from degrees to radians. And here is that method for how we're going to converting from degrees to radians. Okay, radians is equal to, now again, this is confusing, but I want to focus on this part of it right here. This is our conversion, okay, our conversion factor. If you take some physics courses when you're converting miles per hour to feet per second and stuff like that, it's the same process. I do want to point out and remind you that pi radians and 180 degrees are the exact same thing. 180 degrees and pi radians are the exact same thing. So as we go through these, keep that in mind as I work these problems. So we were asked to convert 30 degrees into radians, and here's how we're going to do it. I'm going to multiply by what's called, again, a conversion factor. I know that pi radians, I'm going to abbreviate it with RAD, and 180 degrees is the exact same thing. So what am I actually multiplying by? Well, anything divided by itself is 1. I'm multiplying by 1, so that's legal. So the reason I'm multiplying like this, just a quick reminder, the same way when you're multiplying fractions, you can actually cancel units. And I'm going to cancel my degrees there, and that's the reason. It's very important that you know that. That's the reason that degrees was on bottom here. If it's on top here, you want it to be on bottom here so that it will cancel. So now, what do? I can cross cancel. 30 cross cancels with 180. I can divide both of them by 30. That'd be a 1 and a 6. Now we multiply. 1 times pi radians would be pi radians over 1 times 6 is 6. And I shouldn't draw that line so big. That'd be pi over 6 radians. And just real quick reminder, pi is the same thing as 180 degrees. So this is the same thing as 180 divided by 6, which is still 30 degrees. The next one, 150 degrees, multiply by the conversion factor. I know that pi radians and 180 degrees is the exact same thing. I put 180 on the bottom so that I can mark that out. I can cross cancel by first dividing by 10, which is going to get rid of those zeros. I'm now going to divide by 3, which makes that a 5, makes that a 6. So I'm left with 5 pi on top over 1 times 6 on bottom, 6, and that would be now in radians. And we could turn that into a decimal if we wanted to, but I just want to let you know that most of the time we're going to leave that pi in our radian measures just to make it a little bit cleaner. Negative 220, same method. Pi radians on top, 180 degrees on bottom so that my degree measures cancel. I can reduce by dividing by 10. That gets rid of my zeros. I can now divide by 2. That makes this negative 11, makes this a 9. So that'd be a negative 11 pi on top. All I'm left with on bottom is 9, and that would be now in radian measures. Okay, next up we're converting radian measures to degree measures. And radians, these are in radians. So I want you to think of it like this. Radians is kind of on top here if we put that unit out next to it. So when you multiply by a conversion factor, I'm going to work this the hard way to begin with. There's actually two methods, and this is the harder of the two, but I'm going to go ahead and do it anyway just to show you. So our conversion factor, all that we're doing now is since radians is on top, we're just flip-flopping our conversion factor. I know that pi radians is equal to 180 degrees. Now, why is the radians on bottom now? So they cancel. So what also cancels would be my pi's is gone. What also cancels, 3 and 180, I can reduce that. That'd be a 1 and a 60. That degree symbol is still here. It's not canceled out. So on top you have a 4 and a 60. That would be a 240. The degree symbol stays. On bottom you have 1 times nothing, which is just 1. So you can put a 1 on bottom if you want to, but it's not really necessary. 240 degrees. But again, there is an easier way. Remember that I told you that pi is 180 degrees. So when you're, and this is the reason we normally leave the pi value in there instead of multiplying it and plugging in 3.14, is so that you can very easily convert back to degrees. Look, take out the pi, just put in 180. And what I like to do first is when I clean this up is I always divide first, which is legal. There's no plus or minus sign, so I don't have to distribute the 3. I can, if I want to, I can just do 180 divided by 3, and that would be 60. This would be 4 times 60, which is also 240. So again, the easier way is just take out the pi and plug in 180. So let's try that method here. This would be negative 5 times 180 degrees now over 36. Once you type that in, you can reduce it first if you want to. 180 divided by 36 is 5, so this would be negative 25 degrees. And the last one of these, 7 pi over 4 would be 7 times 180 over 4. You can plug that straight into your calculator and multiply and divide by 4 if you would like to, or you can divide. Some of you will be able to divide in your head. 180 divided by 4, well, I know 180 divided by 2 is 90. So if you divide by 2 again, you get 45. So this is 745s, which is 315 degrees. Now, I do want to take this time. There was a problem that I felt like that we should have went over that's not in this. Sometimes, I told you that sometimes we leave pi in there, but sometimes we don't. Like if I said 3.6 radians. Now, what's actually happened here is there's no pi. We can't take out pi and plug in 180. So if we were to ever have like 3.6 radians and we want to convert that to degrees, now we know that 3.14 pi radians, that's 180 degrees. So I do want to point out that if 3.14 is 180, that 3.6 will be a little bit bigger than 180. So we're looking at probably about a 200 degree angle here, just to give some thought before we start this. But anytime there's no pi in there, you do have to use the other method. 3.6 radians, I know that pi radians, and notice that I put it on bottom so that this happens. I know that pi radians and 180 degrees is the exact same thing. So now what we would actually have to do is in our calculator on top, I have 3.6 times 180, and notice the degree symbol still there. And that's somewhere around 648. And you actually don't have to show this step, but I'm just showing you what I'm doing. 3.6 times 180, the degree symbol still there. On bottom, you have a pi. So what I'm going to do is actually divide, and I'm going to use the pi button, and I get about 206.3 degrees, which is about where we said it was going to be. 3.14 is 180, 3.6 is 206.3. So just a quick reminder, if there's no pi in there that you can just plug in 180, you do have to go the other route. Okay, next part of the lesson, we're going to be talking about coterminal angles. And I'm going to break this down to remind you what we said a terminal side of the angle was. As you rotate, wherever you stop, is the terminal side. You have the initial side, you have the terminal side where it terminates. So if two angles or more are co, if you think about what the prefix co means, it means with or together. So two angles that are coterminal have the same terminal sides. They share a terminal side. So the way that you would get sharing terminal sides, notice here they've graphed a 90-degree angle. And they've also graphed a negative 90, 180, 270, a 90 degrees and a negative 270, or a pi over 2. Remember that pi is 180. 180 divided by 2 is 90. And a negative 390s, it would be negative 270, are coterminal angles because they share the same terminal side. And the way that we find coterminal angles, think of it like this. If I were to take this 90-degree angle, and what if I spin another 360 degrees? I end up in the same place. Or if I spin another 360 or another 360, I end up in the same place. So what we can do is we can either add 360 degrees to an angle, or we can subtract 360 degrees from an angle, and that's going to give me coterminal angles. They're going to be in the same place. So angles in standard position with the same terminal side are coterminal. Give two coterminal angles for each angle, one positive and one negative. So in order to find that, we simply have to add or subtract 360 degrees. And just a quick reminder, 360 degrees in radians, we're about to have to do this, is 2 pi. So if you take 65 and add 360, you get 425. That angle would be coterminal. You take 65 and subtract 360, you get negative 295. And again, if you were to graph all of these angles, they would look like this. Here's 65. 425 would be 360 plus another 65. So it would look like that. And then you have negative 295, which would be negative 90, 180, 270, negative 295. Same angle. So all three of them would look identical. 540, again, we can add or subtract 360. What I'm going to do is subtract 360 since that's a rather large angle. I'm going to get 180 degrees. That's one coterminal angle. However, they said they wanted a positive and a negative, so I can't really add and subtract 360. What I'm going to do is just take and subtract another 360 from 180, and that would give me a negative 180. So all of those angles look the same, and that makes sense because 180 would be here, negative 180 would be here, so they do look identical. Number 12, when you're dealing with radian measures, instead of adding and subtracting 360, we're going to subtract and add 2 pi, which is the equivalent of 360 when you're talking about radian measures. Now, before you can add or subtract, we will have to find a common denominator here. The way we're going to do that is multiply top and bottom by 18 to make the bottoms the same. When I multiply bottom by 18, it makes it 18. Multiply the top by 18, turns it into a 36. So 36 pi over 18 is what I'm adding. When you add it, it gives you a 49 pi over 18. That's my first one. When you subtract 36, that gives me negative 23 pi over 18. That would be my second coterminal angle. And let's try that one more time. 14 pi over 9. We're going to add and subtract a rotation. Common denominator, multiply top and bottom by 9, makes the bottom a 9, makes the top an 18. So when you add 18 pi over 9, you now have 32 pi over 9. That's your first coterminal angle. When you subtract it, you have a negative 4 pi over 9. That's your second one. And just a quick reminder that radian measures right now doesn't make a lot of sense. And notice that here, I didn't even write out radians. If there's no RAD, it's just a number, there's no degree symbol, it's understood that is a radian measure. You actually don't even have to put RAD for radian measures. We just understand that it is a radian measure. But if it doesn't make sense to you, you can always take out pi, plug in 180 degrees, and if you divide that by 9, multiply it by 4, that's actually negative 80 degrees is all that is. So I know that radian measures are not, we're not as comfortable with them, but that's all they are, is a conversion of a degree measure. Okay, next up, we're starting to tie these angles in with this trigonometry and show you how they're related. And the most important concept that we need to learn is a reference angle to make that connection. A reference angle is simply this. It's the angle for, okay, if this is my angle, this is my terminal side, it's simply how far are you from the x-axis, the nearest part of the x-axis. And it'll always be an acute angle, because if you're here, this is how far you are from the x-axis. If you're here, this is how far you are. If you're in this quadrant, this is how far you are. So your reference angle will always be an acute angle. So it's never bigger than 90. So again, for any angle in standard form, the reference angle is the positive acute angle, never negative, formed by the terminal side and the x-axis. Sketch each of these and let's find the reference angle. So number 14, 225 degrees. How far is that from the x-axis? And you'll get to where you can do these in your head without sketching them. So we're at 0. We start here. This is our initial side. We're at 90, 180, 270. So we're somewhere in this quadrant. And where are we in that quadrant is simply we're looking for the reference. How far are we? This is my x-axis. So since we're in this third quadrant, this is the portion of the x-axis we're going to use. How far are we from that x-axis? So what is this angle? And we know that this is 180 degrees. So you're simply pretty much asking how far past 180 are you? And your reference angle there would be, we're 45 degrees past it. Simply subtract it off. Negative 310, let's graph it. We're going to start with our initial side at 0. And since we're negative, we're going in this direction. So we're going negative, let me erase that, negative 90, 180, 270. This would be 360. So we're not going all the way back around to 360. We're only going a little bit past 270. So somewhere right around in there. So how far are we from the x-axis? And again, this is the nearest portion of the x-axis. So how far are we? Well, I know that all the way around would be 360, but we didn't go quite 360. We went 310. Well, how much further would we have went to go all the way around? That'd be 50 degrees. So our reference angle there is 50 degrees. That's how far we are from the x-axis. And again, notice it's positive. Even though my angle is negative, it's positive. Now, here's another trick that you can use. You can always use coterminal angles. So if I were to add 360 to 310, guess what I get? 50 degrees. Now, it doesn't always work out that this is your reference angle, but what you can do instead of graphing 310, well, why not graph 50 and find its reference angle? Okay, number 16, I'm going to be honest with you. I always convert radians to degrees whenever I'm finding reference angles. So 2 pi over 3, I know that pi is 180. Pi divided by 3 will be 180 divided by 3, which is 60. Multiply that by 2, this is 120 degrees. So 2 pi over 3, I know this is 0, where we're going to start. 90, 180, so we're not going to go quite to 180. We're going to be right in there. So the reference angle is going to be this angle. Find the nearest portion of the x-axis, and notice that looks a lot like a linear pair back from geometry. If this is 120, my reference angle is going to be 60. Now, I could convert that back to radians, but I want to point something out. That there is a connection. When I first divided that, pi divided by 3, that's 180 divided by 3, I got 60. So my reference angle, I can just use that. I don't actually have to try to convert it back. But my reference angle is going to be 60 degrees or pi over 3. Okay, for this next section, there's nothing new. I just want to warn you that not to overthink this because it's the same thing that we've been doing. Okay, except for we're going to use a little bit different notation. Okay, it says let theta be an angle in standard position. So we have our theta here. And we're going to let this point, xy, be some point on the terminal side. So we see that we have a point here. So anytime we're talking about a point, okay, in order to plot that point, okay, if the point is xy, that means we're going to have to go over x and up y to get there. Now, what we called the hypotenuse before, they call it an R instead of an H here. And the reason they call it an R is for radius. It's because it's very, very much like a circle whenever you're rotating this this angle around. So we've got some point that's on this terminal side. So we have an x, we have a y, and we have an r, and the relationship between them, you already know, that's a right triangle. So we know that we can relate x, y, and r with x squared plus y squared is equal to r squared, which is actually the Pythagorean theorem. So let me read that again. Let theta be an angle in standard form, P be some point on the terminal side. The distance from P to the origin, which we're going to call r, can be found by using this formula. So not only is that true, but if we go back and review a little bit, if we're talking about the sine, cosine, and tangent of those angles, and we're going to relate this again to those other 200 and 300 degree angles that we've been talking about, the sine of this angle, the sine is going to equal opposite over hypotenuse. It actually equals y over r. So cosecant would be the reciprocal of that, r over y. Cosine will always equal adjacent over hypotenuse. So secant would be the reciprocal of that. And tangent of this angle, now notice that we're not talking about this angle, we're talking about this angle. But it's going to be the same as the sine, cosine, and tangent of this, with the exception of with the positives and negatives is the only thing that's going to throw us off. But the tangent is going to be opposite over adjacent, and we don't have to worry about the whole positive negatives because its location and whether the x's and y's are positive, negative, all that is going to take care of all that for us. So if tangent is y over x, then cotangent will be x over y. So now let's work a problem. If you've got a point 5, negative 2 on the terminal side, so let's actually graph that. So we're going to go over 5, we're going to go down 2, so it's somewhere down in here. So let me zoom in and actually draw that. So here's my y value, here's my x value. This is what we referred to as a reference angle a while ago, but we've got some angle here. Let me draw it. There's the terminal side, so there's my angle. So if 5, negative 2 is a point, so this is 5, this is negative 2. We can actually do Pythagorean theorem, a squared plus b squared equals c squared, and we get the square root of 29 will be our hypotenuse. And we can find, just find the exact values of the trig functions of theta. So let's do that. So the sine will be opposite over hypotenuse, which would be negative 2 over root 29. Which we always rationalize that. Let's multiply the top by root 29. Let's multiply the bottom by root 29, and that's what we get. The cosine is adjacent over hypotenuse, which will be 5 over root 29. Multiply top and bottom by root 29. You get 5 root 29. You just leave it over 29. There's the cosine. And then finally, the tangent would be the opposite over the adjacent, which would be negative 2/5. And that would be the tangent. Now to find again the cosecant, secant, and cotangent, we simply reciprocate those. But let me show you a trick. To find the cosecant, do not flip this, because what that's going to do is put the radical back on bottom. Why not? Flip this instead. They're equal to each other. And that'll be a negative, because the 2 is negative, root 29 over 2. Same way with the secant. Let's reciprocate this. That gives you root 29 over 5. And then the cotangent would be negative 5 over 2.